In the last two videos, we motivated the singular value decomposition, or SVD, and then we showed how we can actually get the singular value decomposition of a general matrix A. We did an example, and now we want to look at it from a vector point of view. So if you remember from the previous video, we framed singular value decomposition in the usual way as U times sigma times V transpose, as this matrix product, matrix factorization. Now we want to find an equivalent vector form of that, and that's going to help us to see and suggest some applications of how we can use SVD in various settings. So to do that, let's write out our singular value decomposition. Again, U sigma V transpose. We'll write it out in this form, but I want to actually do the matrix multiplication to show you that we get this final form here, and I'll walk us through that relatively quickly. You can go through and look at these details and convince yourself that this is right on your own. But here's U. So again, it has the left singular vectors as its columns. Sigma, here again I've shown it with m being less than n, either way is fine, and it has the singular values down the main diagonal. And then V transpose, which has the right singular vectors as its rows, because we've taken the transpose. If I first take this matrix product, U times sigma, again, you have to look at this, but you can convince yourself that it's actually equal to this. There's a big block of zeros here on the right for this particular case, m less than n. And the first column is simply sigma 1 times U1, second column is sigma 2 times U2, all the way through to m, and then all the others are 0. If we further multiply by V transpose, once again, if you look at it carefully, you can convince yourself that the result is going to be the sum of these vector products. So sigma 1 U1 V1 transpose, sigma 2 U2 V transpose, and a term for each of those non-zero singular values up to, say, P. Now this U1 V1 transpose and U2 V2 transpose and so on, this is actually an outer product. If you remember from chapter 1, we introduced inner products. We use inner products all the time. We call them dot products, inner products, scalar products. We also introduced the idea of an outer product, and we said this will come up sporadically, but not very often. This is an outer product. So remember, an inner product of, say, x and y would be x transpose times y, or y transpose times x. So the transpose vector comes first, and then the non-transpose vector. If you switch the order, so say U1 V1 transpose, now that becomes actually a matrix. U1 is m by 1. V is a row vector. That's 1 by n. So the end result of that matrix multiplication is going to be an m by n matrix. So these outer products produce a matrix of the same size as the original A matrix. Now this starts to suggest some possibilities. So you can think, for example, of reconstructing A. So if we had a singular value decomposition of A, we could reconstruct A by taking these vector products and adding them up. But now imagine that some of those singular values are small. So say the last number of them are very small, or maybe even 0. There's no need to include those terms in that sum, that vector sum that we see up here. All right, so that gives us some ideas. What if we had a large data set and we do the SVD, and it turns out that most of the singular values are actually quite small, very close to 0. Remember, they're never negative, they're always 0 or positive. And what if many of them are very, very small? Well, we could get rid of those terms that correspond in the vector sum here that correspond to those small singular values, reconstruct the A with any number of the terms we want, presumably the ones with the larger singular values, and we can reconstruct an approximation of the full data set A. So in that sense, we're reducing the information required, because we only need the sigmas, the u's, and the v's for the terms that we keep, that give us a reconstruction of A that is reasonable or accurate in some sense. That's the basis of proper orthogonal decomposition. You've heard me mention this a number of times. Again, it's not until chapter 13 that we get into the details of POD, but it's based on this very idea. In fact, many people think of SVD and POD as kind of synonymous in this very sense. So take a large data set, reduce it down to a much more manageable size, but still have a fair representation, an accurate representation of the original data with this reduced amount of information. To illustrate these ideas, let's take a very interesting matrix. It's called the Hilbert matrix. It looks very simple. It looks innocuous. You would not think anything of it, but it turns out that it has some very interesting properties. So as an illustration, here's a 5 by 5 Hilbert matrix, and you can see these are ones, halves, thirds, fourths, fifths, sixths, sevenths, eighths, and ninths. Now you can start to see what's happening as this gets bigger and bigger and bigger. These additional diagonals get smaller and smaller. But nevertheless, let's take a look at this Hilbert matrix and see how it behaves in the context of an SVD. And again, with this idea of reconstructing the original matrix, in this case the Hilbert matrix, from a subset of the information that we get from the SVD. So let's take a 40 by 40 Hilbert matrix. So the same, but extended out to be 40 by 40. We do the SVD, do this in MATLAB, Mathematica, and so on, and you get the U, you get the V, and you get the sigma, all of which are 40 by 40 to start. So the full reconstruction, or the full SVD of the original Hilbert matrix comes from 40 by 40 U, 40 by 40 sigma, 40 by 40 V. But if you take a closer look at the singular values themselves, you'll see a very interesting behavior. So here I've plotted the values of the singular values, the sigmas, with n. So capital N is 40, so little n goes from 1 to 40. So the largest singular vector is this one, second largest is this one, third, sigma 4, sigma 5, and I'm showing the first 15. So sigma 1 through sigma 15. Sigma 16 through 40 are all 0. All right? So these are the 15 non-zero singular values. So the first thing I think about is, okay, well, I actually only need 15 of those terms, sigma times U times V transpose terms, in order to get a reconstruction, in fact, a full reconstruction of my 40 by 40 Hilbert matrix. So right there we have a good reduction in the amount of information we need. However, if you look even closer, I've plotted the sigmas on a log scale. So these sigmas over here are actually quite small. These are 10 to the minus 5, 10 to the minus 6, 7, 8, 9, 10, 11 kinds of numbers. So these sigmas are actually very, very small, and they contribute, or their terms contribute very little to that reconstruction. So this suggests the possibility of just keeping maybe the first 5 or 10 of these singular values and the corresponding terms in the sum in order to reconstruct the Hilbert matrix. Here's another way to look at that same behavior in the singular values. What I've plotted here is the cumulative sum of the singular values versus n, all the way up to 40, the size of the matrix. So this first point is the value of sigma 1. The second is the sum of sigma 1 and sigma 2. Then sigma 1, 2, and 3, 1, 2, 3, and 4. So we're adding just one of the additional singular values to the sum as we go from point to point. And what you'll see is it levels off very quickly. So these additional singular values are adding very little additional information about the nature of the data, or in this case, our Hilbert matrix. So once again, if I were just to keep the first several of these, say 5 of these, I would expect to get a reasonably good, reasonably accurate reconstruction of my original Hilbert matrix. So if you do that, I won't show the details. This is great to play with. Set it up in MATLAB, set it up in Mathematica, try different size Hilbert matrices, and try different reconstructions. So with 1, 2, 3, 5, 10 of those vector product terms. So let's reconstruct our H. In vector form, I'm just going to keep the first K, capital K, of those vector products. Okay? In matrix form, you can think of it as follows. So we're reconstructing our original Hilbert matrix. It's U sigma V transpose. But what we're going to do is we're going to get rid of some of the information in U some of the information in sigma, and some of the information in V. So if I only keep capital K of the modes, then U would be 40 by K, sigma would be K by K, and V would be 40 by K. All right? So we've literally gotten rid of columns of U and columns of V, as well as columns of sigma. And we've thrown away the corresponding sigmas, U's, and V vectors. So if we only had n is equal to 15, remember 16 through 40, the singular values are all 40, so those terms don't provide any additional information. So if we had capital K was 15, we would get back an exact full representation of the original Hilbert matrix, because no information is lost, even though we have only kept 15 of the modes versus all 40. More to the point, with regard to applications like POD, even for some of these, in fact many of these additional modes, this corresponding singular values are extremely small, and they contribute very, very little to the overall information contained in this reconstruction. So for example, if you were to take K as 5, so just the first 5 of the 40 modes, you could reproduce the 40 by 40 Hilbert matrix within 5 significant figures. And you can decide how much accuracy you need in this reconstruction. And if you need more accuracy, you include more modes. If you don't need as much, you can include fewer modes. But the point being, I only now need to store 5, in this particular case, 5 sigmas, 5 U's, and 5 V's, rather than all 40. So much less information needs to be retained, and I can get a good reconstruction, a reasonably accurate reconstruction of the matrix. Now let me say just a few things to kind of summarize this discussion about singular value decomposition. You'll notice we have not made any assumptions about A. So A can be square, rectangular, it can be real, and in fact it can be complex, even though we've been focusing on the real case. So this SVD applies to any matrix. And it's pretty remarkable in that context that any matrix can be factored, can be decomposed into the product of 2 orthogonal matrices and a diagonal matrix. I mean, it honestly could not be any better than that. And once again, this is really in marked contrast to the previous operations that we've looked at, where we had all these special cases, right? So if I want to take a determinant, well, the matrix has to be square. If I want to do the inverse, the matrix first of all has to be square, and the determinant has to be non-zero so that it's non-singular, and so on. So there's just all these requirements, all these conditions that have to be met for many, many, many of these operations. SVD is one of the few operations you can do literally on any matrix. So this is very, very powerful. And this therefore opens up a number of very powerful applications. So let's start by looking at just the simple matrix inverse by itself. So the matrix inverse, remember, strictly speaking, only applies for square matrices that are non-singular, so they have non-zero determinants. Well, let's think about how the SVD could be used to express such an inverse. So for the matrix inverse to exist, the rank of A has to be equal to n, where n is the size of the square matrix. So A won't have any singular values that are 0, and we can take advantage of the orthogonality of U and V to express the matrix inverse in a rather interesting and useful way. We're going to denote it by a superscript plus. So A plus, some people use a dagger sign. So that's the inverse of the SVD of A. So let's just take a look at what that is. So remember again, the inverse of the product of matrices is the product of the inverses in reverse order. So we have V transpose inverse, but V is orthogonal, so the inverse and the transpose are the same. So V transpose inverse is just V, sigma inverse, and then U inverse, but again, U is orthogonal, so transpose and inverse are the same. So we can write the inverse of A as V times the inverse of sigma. Now let's think about that. Sigma, in this case, would be a square matrix, which is diagonal, and the inverse of a diagonal matrix is a diagonal matrix with the reciprocals of the diagonal elements on the diagonal. So that gives us a way that we could express the inverse of a square matrix in terms of its SVD. Now, what makes this even more powerful is when we generalize this definition to any matrix A. And that's why we use a different notation for it rather than a to the minus 1. So this same definition for any real A could be regarded as an inverse. We actually call it the pseudo-inverse because it's like almost an inverse, or people call it the Moore-Penrose inverse to honor those that developed this. And this applies to any matrix. So whereas the inverse itself only applies to square matrices with non-zero determinants and so on, the pseudo-inverse, denoted by A plus, can be written in terms of SVD in this way. And that again applies to any matrix. So now we have, in a sense, a generalization of the inverse that can be applied to any matrix. So this gives us a way to quote-unquote solve systems that normally we think of in a chapter 1 sense don't have a solution. So if you have, say, an overdetermined system, an overdetermined system means you have more equations than you do unknowns, so it's overdetermined. There are too many equations for the number of unknowns. You can quote-unquote solve that. Now we have to define what we mean by a solution of such an overdetermined system. But you can solve that by using this pseudo-inverse. And in fact, it looks very much like the chapter 1 inverse. So the solution U would be the pseudo-inverse of the original matrix A times the right-hand side vector B for an overdetermined or a tall, skinny matrix A. So this is going to become useful in part 3 of the book, and we'll use this extensively. Let me make a number of comments about the SVD. First of all, we have not been emphasizing this, but there is a SVD for complex A. The only difference is that you need to use the conjugate transpose instead of just the transpose of V. Otherwise, everything is the same. I'm just going to mention a few of these remarks. If you think back to chapter 1, really the main diagnostic that we had for a matrix to determine whether we could solve a system with that matrix as its coefficient matrix and so forth was the determinant. And remember, it was really binary. So either the determinant was 0 or it's non-zero, so therefore it's either singular or non-singular. And there was no gradations in between. So now let's imagine we want to solve a problem, a very, very large problem with thousands or maybe even millions of unknowns and equations. And let's say the determinant of the coefficient matrix is not equal to 0, so it's not singular, but is very, very small. And the question is that okay? So it's not singular, so I can take the inverse, and if I do so, I get a result. But the question is that an accurate result? The determinant only tells you whether that matrix is singular or not, whether it can be invertible or not. It doesn't tell you how accurate that inversion process is going to be. So rather than the determinant, it's helpful to use what's called the condition number for a matrix, and that tells us very specifically how accurate such an inverse or any operations like Gauss elimination will be on that matrix. For 2x2, 3x3, 4x4 small matrices, this is not terribly important. But again, in engineering and science, we're going to be thinking about thousands and millions of equations and unknowns. So these systems become very, very large. If the system is what we call ill-conditioned, and so the condition number is in fact very, very large, then it turns out that that means that when I do the inverse, if I do Gauss elimination, I expect to see very detrimental effects of round-off error in those operations. I expect to get a result that is not very accurate. And in fact, the condition number gives us a way to estimate how much accuracy is lost. And all that is given in part 3. Well, the condition number is based on the singular values of the matrix. So from the SVD, we can determine the condition number. From the condition number, we can determine whether it's well-conditioned or ill-conditioned, and whether these standard operations are going to be successful or not in terms of giving us accurate results. So finally, let me list a number of applications. I keep making this claim that SVD has applications all over the place. Let me just list several of them here. So the first is least squares curve fitting. I kind of alluded to this a moment ago. Least squares curve fitting is a topic we'll discuss in part 3, and it can be put into an SVD framework. You don't have to put it in that framework, but you can put it in an SVD framework, which is actually quite helpful to see how it relates to these ideas of data reduction that we've been talking about. We can also use it to determine orthonormal basis vectors that is much more effective, much more accurate than was the case for Gram-Schmidt. If you think back to chapter 1, Gram-Schmidt, it was the step-by-step procedure, right? So you have a first vector, you take the second vector, and you do some operations that make it orthogonal to the first. Then the third one, you do some operations that make it orthogonal to the second and the first. And then every subsequent vector is made orthogonal to each of the previous vectors. Again, for 3, 4, 5 vectors, that's fine. Gram-Schmidt is perfectly fine. But if you get into the hundreds or thousands or even millions of vectors, then the round-off errors that can accumulate in that process can be quite detrimental to getting an accurate result. So one alternative, a very useful alternative, is to use SVD to get those orthonormal basis vectors. Once again, the U and the V modal matrices give us a set of orthonormal vectors. I'm going to look at an example in the next video of image compression. Image and signal compression are very important applications where SVD can be used for compressing the amount of data that's required to reconstruct an image or reconstruct a signal. We'll talk about that in the next video. I keep mentioning POD. It also goes by the name principal component analysis as well. We can also use the pseudo-inverse to solve ill-conditioned systems. So if once again we have a very large system that's ill-conditioned, has a large condition number based on the singular values, so we expect that doing inverses and Gauss elimination and various operations on that matrix are going to be inaccurate. So we can use the pseudo-inverse as a way to get a more accurate solution. It can also be used in optimal control in transient growth of linear systems, which are topics that are discussed later in the book as well.